class. We are here in this video to look at Chapter 3 that I didn't quite have time to cover. But I think the video will actually be a better way to give you this material because you're able to pause it and use as much time as you need to get this down into your notes. There's a lot here to write down, so I think this is actually maybe a better option. But if you have questions, please don't hesitate to tell me. Let me know. I'll be glad to help you. We just have a lot of definitions to look at here. So I'm going to go to my glossary, which is the last chapter in the book, and we have already added a lot of terms. But these are the terms that we need to add for this chapter. So there you can see there are a lot of them. And I'm just going to pick up where I left off the last time with the first term, and that term is Xintercept. Now we've talked about this one just briefly as we've gone through some of the problems, but I want to give you the actual definition from the HiSET book for your flashcards. The Xintercept is the X coordinate in a point where a graph touches the x-axis. And I'll draw you an example here. So let's sketch a coordinate plane. And I'm going to change colors to put my graph in. I'm going to just draw a linear graph that comes down like this. So it has a negative slope. And we're interested in that point, that spot where it crosses the x-axis. Right there is the x-intercept. And maybe that point is at 2. So the run is 2 and the rise is 0. And that is called the x-intercept. That's the point. But the actual intercept is the number 2. It's the spot where the line crosses or touches the x-axis. And when you're looking for an x-intercept, here's a good thing to keep in mind. The y value of the point must be 0. So if you're looking at a table of values and you find a y value that is a 0, the input that goes with that is the x-intercept. Y is 0, and then x will tell you where it crosses the line or touches the line. So we've done x-intercept. Let's look at positive interval. This is not one that we've talked about. When you see the word interval in a math book, or really anywhere, you can think of the word section. So this is the positive section of a graph. And the positive interval is the values in the domain. And remember, those are x values if we're talking about a domain. The values in the domain, or the x values, for which a graph is above the x-axis. So here is another example. Let's sketch a coordinate plane, and this time I'm going to use a parabola. We're going to use a quadratic graph that opens upward. So I'm going to sketch my parabola right in there, and it does that every time. Let me turn off the... So something like that. Okay, so we know this is the x-axis, and we're looking at those values of x where that graph is above the x-axis. So let's look here to see where that would be. Now here is, maybe let's let this be x is 2. Actually, let me do it this way. Let's use a coordinate. So let's say x is 2, y is 0. Over here we have maybe x is negative 2 and y is 0. So we have two x-intercepts. So we have to look at where the x values would be positive for this graph. And this is a little bit tricky to see. You want to focus right here. Here's where the graph is above the x-axis, and that is between, actually no, I'm sorry, it's when x is more than 2 or when x is less than negative 2. Okay, we are not looking at the values in here just yet. We're looking at those where it is above the x-axis. So the positive interval in this case would be written like this. If you want to write it in proper math terms, you would say this: the positive interval, or the positive section, is when x's are bigger than 2 or when they're smaller than negative 2. And then in the next one, I'm going to just copy this. We'll use the negative interval. I'll show you. Let me just go ahead and copy this for the next page. And that will be our next term. So let's go ahead and flip on over. We'll define the negative interval. And I'll tell you what, just to reiterate how very similar these are, I'm just going to change out my wording. So this is the negative interval, or the negative section. It is the values in the domain for which the graph is below the x-axis. And we already defined our positive interval. That was on the last one. I'm going to leave the diagram alone, and I want you to focus with me in this area. It's where the graph dips below the x-axis. So it would be this point and this point and this one. So it's when x is between those two dots that things are below the x-axis. So to define that mathematically, we would say that the negative interval is when x is less than 2 but greater than negative 2. It's that green area in there. And let me just color that in. Maybe that would help to see. Here's the negative interval. Okay. And then back on this one, let me color in that positive interval for you. I'm sorry, I'm doing that again. It's this area where the x's are outside of that boundary line. They're above the x-axis and past those two intercept points. This is not going to be that critical. It's just in the book and wanted to show you, but I wouldn't worry too much about those two. Okay, let's look at decreasing interval and see if we can get a mental image of what this one looks like. A decreasing, which you know that word means it's getting smaller. The decreasing section is going to be values of x. So we're dealing with those input values for which a graph falls from left to right. And I'll draw you a picture. Pictures are worth 1,000 words on these. It is where the values of x, the graph falls from left to right. So I'm going to use a parabola again, and I think I'm going to use one graph for two definitions. So let's put it right here. Alright, and I'm going to draw myself a parabola, or try to. These are tough to draw on this thing. So here we go. We'll just keep him opening upward. That's fine. Alright, so if you look at this parabola, and remember here is left and here is right, just like we read. So let's see what's happening right here. You see how that graph is falling from left to right? It's dropping from left to right. That's the decreasing interval. It is in here where the graph is falling, and then it makes its turn and it starts to increase. So there is the increasing interval. And I'm just going to go ahead and give you that definition right here. So these would be values of x for which a graph rises, increases from left to right. Climbs. Any word that you want to use is fine. I like rises. So that's the green interval that I drew there. So we have decreasing, and then we get a turn, and we have increasing from left to right. Okay, let me go back and get my next terms. I had decreasing interval, increasing interval, relative minimum, and maximum. We talked a little bit about minimums and maximums, but let me give you the definition. And we're just going to combine these. Did I combine them on your... I can't remember, guys. If I didn't, you can separate them on your flashcards. I can't remember if I put them together or not. But I'll give you the way to write it in case I didn't. Relative max and min refers to the y coordinate, because minimums and maximums relate to height and depth. So we're talking about y coordinates of any point that is the highest if you're talking about a maximum. So I'm doing minimum and maximum, so I'll put lowest and highest. Point for some section of a graph. and I will show you some examples. Let's take a coordinate plane. And this time we haven't defined this term yet, but I'm going to use a periodic graph just to show you maximums and minimums. This is a wavelength graph. So we get this motion of repeating patterns, if you will. Pretend that those are all the same. Actually, let me try something here, because they really do need to be the same. Let me delete this out. And we'll define periodic graphs in just a second. But with a periodic graph, you get this pattern that repeats over and over, like a sound wave or an earthquake wave. You get those repetitions. So I'm going to try to build this one so it will be exactly what I'm looking for, kinda, sorta. Okay, and this is going to help us illustrate that concept of minimum and maximum. So let's draw the coordinate plane. I'll let y be right there. So here's x and here's y, and I have this periodic graph. Another example of this would be an EKG. If you are going into the health field, you'll have to look at minimums and maximums to interpret blood pressure and heart rate. It's a real good practical example. But here's a minimum. A maximum. There's a minimum, a maximum, a minimum, and a maximum. So these are max and min. You can have more than one on a graph. Just depends on the graph itself. If you're talking about science, these are called crests and troughs. If you're looking at wavelength. So this is called a crest, and this is called a trough. And the closer the maximums are to each other, the faster the wave is moving. You can measure wavelength using maximums and minimums. But we're looking at parabolas and different kinds of graphs that could have max and min. For example, this parabola has a minimum because it's opening upward. It's a smiling parabola. So this is a minimum. It's where the turn occurs. So those two at least are kind of common sense. Maximum, minimum. Alright, let's see. We got relative maximum and minimum. We have end behavior. End behavior, and I need a new paper. I hope I gave you enough. If not, just add a sheet of notebook paper. It'll be fine. Let me erase what I've got here. End behavior is focusing our attention on the ends of a graph, on the where the line starts and stops. So end behavior. This one is kind of almost so obvious that it's unnecessary, but the textbook uses it, so I will also give it to you, the definition. End behavior is the appearance of a graph as it extends in both directions away from zero. And we're going to look at some problems that involve end behavior. We'll talk about that a little bit more as we get further in. Okay, let me copy this so I don't have to keep flipping over. The next one is symmetry, and this is an important one. Symmetry is a very important concept in math. or a line of symmetry. I can't remember how I gave it to you, but either way, it's fine. It's going to mean the same thing, a symmetry line or a line of symmetry. Is when a line, and it may be an imaginary line or it may be an actual line. So I'm going to say an imaginary or real, either one, divides a figure into two halves that are mirror images of each other. Okay. And to illustrate this one, rather than using a graph, a parabola, or a linear equation, let's take a look just at a regular shape. Okay, and I like a rectangle because I can get this to work several ways. So let's take a rectangle, something like that, and I'm going to copy it so I can have an exact duplicate of that. And let's draw a line of symmetry. I'm going to turn this into a red line for the line of symmetry. So let's suppose that I drew a line right down the center of that rectangle, right there. And that I folded the rectangle, and it's not exact, guys. I'm having a little trouble getting this. I folded the rectangle on the red line. I have mirror images. Okay, so we would call this a line of symmetry. Okay, what if I took the same rectangle and I divided it right here, and I fold it on that line? It would have two identical halves. It's like a mirror reflecting the other half. So this is a line of symmetry. Okay. Lines of symmetry will give you two identical halves. And some shapes don't have lines of symmetry. Some do. All right, our next, oh dear, I cut it off, didn't I? And I think I erased over it. Let me try to remember. I know rotational symmetry is one of them. I may have to go back to the text to get the others. Rotational symmetry. So this one is when a figure can be rotated or turned less than a full circle, less than 360 degrees. Around a point, and coincide with itself. I need a video to show you this one. That is called rotational symmetry. And I'm going to stop this video and see if I can find an illustration online to show you rotational symmetry.